this lesson, we'll learn how to add and subtract rational expressions that have like denominators. That's when the denominators are the same for both of the expressions. First, I want to review addition and subtraction of just regular fractions. Here we'll add a couple of fractions and then simplify to the lowest terms. Since they have the same denominator, it's quite easy. We have 1/2 plus 1/2, so it's 1 plus 1 all over 2, which is 2 over 2, which simplifies to be 1. Again, here we have like denominators, so we add the numerators, and the denominator stays the same. 3 plus 5 is 8 over 10, and 8 over 10 will simplify. There's a 2 that can come out of this and out of this, so we're simplified as 4/5. Here we're subtracting fractions. They still have the same denominator. So 7 minus 3 all over 24. 7 minus 3 is 4 over 24. Now you can see we have a common divisor of 4. So we're going to take out that factor of 4. Once there, 6 times there, and we're left with 1/6 as a simplified answer. Now we're subtracting and adding fractions together. We'll go 11 minus 5 plus 1 all over 36, since the denominator is the same. 11 minus 5 is 6 plus 1 is 7 over 36. There's no simplifying there, so that's your answer. Now we're going to look at sums and differences of rational expressions. To add two rational expressions with like denominators, we add their numerators. Keep the same denominator. Very similar to what we did when we were working with plain fractions. So a over c plus b over c will be a plus b over c. A over c minus b over c equals a minus b all over c. And of course c is non-zero. So when I'm adding these, I will add the numerators and keep the denominator the same. So I have 3 over x, and that is simplified to lowest terms. Here I have a denominator 4x for both of them, so I simply subtract that second numerator, and it's all over 4x. Simplify by subtracting the 7 from the 7, so I just get a 2x on top and a 4x on the bottom. I can simplify by canceling there and canceling there, and that leaves me with an answer of 1/2. Again, I'm subtracting and I have the same denominator, so I subtract the numerator and keep the denominator the same. Let's simplify. 5z minus z is 4z over 4z plus 3. Now, can I cancel this 4z with the 4z on the denominator? No, I can't do that, because this 4z is connected to that 3 by addition, not by multiplication. So it's not a factor, it's a term, and we don't cancel terms. Here let's add t plus 5 plus t plus 7 all over t plus 6. So I have a 2t plus 12 all over t plus 6. Now I cannot cancel anything because I don't have it factored. I can factor that numerator though, so let's factor that as 2 times t plus 6, and the denominator is t plus 6. Now you can see we cancel the t plus 6, and we're left with a 2 over 1, which is simply 2. On this problem, we're subtracting, but we have the same denominator. Now this one is going to be a little tricky. You'll have to remember this when we subtract fractions in the future. We have x squared plus 4x minus 1, and I want to subtract all of this. So I'm going to subtract and make parentheses so I am sure to subtract the entire numerator. The denominator stays the same, and now that makes a big difference. We get a minus x squared, a plus 4x because we're distributing that negative, and a plus 5 all over 4x plus 2. Let's collect like terms. X squared minus x squared cancels out. We have 4x plus 4x is 8x. We have a negative 1 plus 5 is plus 4 over 4x plus 2. Now if I want to simplify this, I'll need to factor. I cannot cancel things unless I have factors. So I'll factor here. Factor out a 4 on the top, and you're left with 2x plus 1. Factor out a 2 on the bottom, and you're left with 2x plus 1. Now you can see the 2x plus 1's cancel, and 2 goes into itself once and into 4 2 times. So our answer is 2. Let's define what a least common multiple is. For instance, if I have the numbers 6 and 8, I can write out the multiples of those numbers. 6, 12, 18, 24, 30, 36, 42, 48, and so on. I can write out the multiples of 8. 8, 16, 24, 32, 40, 48, and so on. Now, if you look at the common multiples, they have 24 in common, they have 48 in common, and they'll have infinitely many common multiples as we go out this way. Now the smallest of those, or the least of those, is 24. So the smallest number that 6 and 8 will both go into is 24. Kind of a humorous application where least common multiples could be used are the example of hot dogs and hot dog buns. Hot dogs often come 10 to a pack, and buns come 8 to a pack. So the question here would be, what is the least number of hot dogs and buns you could buy and still use every hot dog and bun in the pack? So if we find 8 and 10, we don't just multiply those together, we'd have 80 hot dogs. What is the smallest multiple they have in common? We could go ahead and write out the multiples like we did in 6 and 8, or we could use a strategy where we factor both of the numbers. Let's go ahead and try that. So if I factor 8, it's 2 times 4. 4 is not prime, so we must factor it as 2 and 2. 10 is 2 times 5. 2 and 5 are both prime. So we finished with the prime factoring of 8 and 10. Now what we'll do is write the prime factors that show up, and we want to use them the most number of times that those prime factors occur in one set. Here we see that the factor 2 shows up 3 times here and once here. We want to use it 3 times, the most number of times that it occurs in one set. 5 shows up once here and none here, so we'll want to make sure that we use 5 just once. When I multiply that out, I get 8 times 5, which is 40. 40 is the smallest number that 8 and 10 will both go into. Here is the strategy for finding the least common multiple outlined for you. Let's go ahead and practice some more. If I have the numbers 4 and 6, I'll find the prime factorization of those numbers. 4 is 2 times 2, 6 is 2 times 3. So the prime factors I have are 2 and 3. How many times will I use 2? It shows up twice here and once here. I want to use it the most number of times it occurs in just one of those sets. It shows up twice at the most. 3 is used once here and no times here, so we want to make sure that we use it just once. When I multiply that out, I get 4 times 3, which is 12. So 12 is the smallest number 4 and 6 will both go into. With 32 and 40, we can use the same strategy. Unlike the numbers 4 and 6, the numbers 32 and 40 are a little more difficult to just think about what the least common multiple might be. Let's find the prime factorization. This is 2 times 16. 16 is 4 times 4. And both of those 4's are 2 times 2. 40 is 2 times 20. 20 is 2 times 10. 10 is 2 times 5. So the prime factors I have are 2 and 5. What is the most number of times that 2 occurs in one set? 1, 2, 3, 4, 5 times here, or 3 times here. I need to use it 5 times. 5 shows up just once there, no times there, so I'll use it once. So I have 32 times 5, 160. Finding the LCM of polynomials is a similar process. Let's find the least common multiple and leave the answer in factored form. With 4x, it factors as 2 times 2 times x. 6x factors as 2 times 3 times x. The factors I have are 2, 3, and x. How many times will I use 2? It shows up twice here, once here, so I'll use it twice. 3 shows up once here, no times there, so I'll only use it once. X shows up just once there and once there, so I can only use it once. When I multiply these together, I get 12x. 12x is the LCM of 4x and 6x. Now with 5x and 10x squared, 5x is already factored. 10x squared is 2 times 5 times x, or you can just write x squared and know that we have 2 x's in that set. So the prime factors here are 2, 5, and x. How many times can I use 2? Once. How many times can I use 5? Shows up once here and once here, so just once. And how many times will I use x? It's once here and twice here, so I'll want to use it twice. When I multiply that, I get 10x squared. You can also see 5x goes into 10x squared. 10x squared goes into itself, so 10x squared is the LCM. Whenever one of your numbers goes into the other number, the larger number is your least common multiple. Let's try with this one, x and x plus 1. X and x plus 1 are our numbers we're finding the LCM for. X is completely factored. X plus 1 is completely factored. If it helps you to see that this is all one number together, go ahead and use parentheses. I'm going to list my factors. And how many times will I use x? X shows up once here, and there's not a plain x over here, only an x plus 1. So once here, no times here, I'll use it just once. X plus 1 shows up once here, and no times there. So this is our LCM. Remember, if two numbers are prime, then the LCM is just the product of those two numbers. This would be similar to the numbers 2 and 3. They're prime numbers, so the LCM is multiplying them together and getting 6. Here we have x squared plus 2x and x squared. We have to factor so we know what each polynomial is made of. So we'll factor out an x here. We're left with an x plus 2. X squared is already factored. The factors that show up are x and x plus 2. How many times will I use x? X is used once here and twice here, so I'll need to use it 2 times. X plus 2 is used once here and no times here, so I'll use it once. This is my LCM. Let's try this problem. 3y squared plus 6y, I first need to factor. We have a greatest common factor of 3y that we can take out, and that leaves us with y plus 2. With 3y cubed plus 3y squared minus 6y, I also have a greatest common factor of 3y that I can pull out of that trinomial. That leaves me with a y squared plus y minus 2. Now does this factor? Yes, it factors as 3y times y plus 2 times y minus 1. Now let's go ahead and list our factors. How many times is 3 used? Once here and once here, we can only use it once. Y is shown here once and once, we can only use it 1 time. Y plus 2 shows once and once, we can only use it 1 time. Y minus 1 shows up once here and no times here, so we'll use it once. This is the LCM of those 2 polynomials. Now let's diverge to rewriting rational expressions so that we have a desired denominator. For example, if we have a fraction 1/4, but we want the denominator to be 8, we would change it to be 2 over 8. How do we do this? Let's say we have 5/7, and we want to rewrite this so that the denominator is 21. How did 7 become 21? It became 21 because we multiplied it by 3. But if we multiply the bottom by 3, we also have to multiply the top by 3. That way, we're multiplying by 3 over 3, which is just multiplying the fraction by 1. It will not change the value of that fraction. So 3 times 7 is 21. 3 times 5 is 15. Now you can see that this will not change the value of your fraction. You can grab your calculator and put in there 15 divided by 21, and you get this decimal. If we take 5 divided by 7, you get the same decimal. 2x over x plus 1, but we want the denominator to be x squared plus 2x plus 1. So let's see what we have here. First, if we want to know what this is made of, wouldn't we have to factor it? It factors as x plus 1 times x plus 1. How did we turn x plus 1 into x plus 1, x plus 1? We multiply to n another x plus 1. So we have to multiply the top by x plus 1 as well. So we can keep this in factored form, and that is your fraction. Go ahead and try the homework and let me know if you have any questions.